Here again. This is part 3 of our discussion of comparative statistical tests. In the last discussion, we were talking about our t-tests. Remember, t-tests compare the means of two groups. We noted that if we don't have scale data, we use their non-parametric equivalent, which for the independent samples t-test was the Mann-Whitney U, and for the paired samples t-test it was the Wilcoxon test. And for the independent samples t-test, if we have nominal data, we use chi-square. And for the paired samples t-test, if we have nominal data in that pre-test, post-test design, we use a version of chi-square called the McNemar. I left off showing you the output we get from SPSS for a chi-square. I want you to notice something here. For the chi-square, if I run a chi-square in SPSS, this is exactly what I get. This was a study that I was working on with a student, and I ran the data. This is what we got. I want you to notice that in all of this output, and this is all we get, there's no R value. We have the number of participants. We have the total number of participants, the maybe cases that were incomplete. We have what I refer to as the cross tabulation, showing the number in each of these different categories and if they were satisfied or not, and the total of that. Then we had several different types of chi-squared. We get a value, degrees freedom, and in another class I talked about how we use those two to determine our p-value. And so we got these p-values for different types of chi-squares that we can run, but also that almost all the time, maybe 99% of the time, we use Pearson's chi-square. I didn't mention, some of these are a little bit more conservative. Some of those that developed these thought that Pearson's chi-square was a little bit too liberal, so you'll see their p-values are higher. Others thought that the chi-square was fine, but they wanted to calculate it a different way. So anyway, we get a p-value, but there's no R value here anywhere. And the reason why I mention this is that in some places you will see the chi-square test. Notice a test of association. But with association, we need an R value to show what that association is. And I would suggest to you that all we have here is a real difference. And because it's a difference in the frequency of two nominal events, or it can be more than two nominal events, but because it's a difference, I classify it here with a comparative test. So just to let you know that if you see this mentioned as a test of association, I don't consider it to be that. I consider it to be a comparative test showing the difference in these the frequency of these nominal events. With the t-test, we do have some limitations. All the t-test can do is compare the means of two groups, and again, the Mann-Whitney, the Wilcoxon follow that same thing. They can only compare the medians of two groups. But none of these can compare three different conditions in an independent variable at the same time. But the one-way ANOVA can. In fact, the one-way ANOVA can compare many think an unlimited number of groups at one time. So if you want to, you can think of the t-test as being a test that cannot multitask, and an ANOVA, on the other hand, as being the expert multitasker. So let's look at this example. Again, we're studying weight loss. We have two diets. One group gets one diet, say the keto diet. The other group gets a second diet, maybe the regular diet. We record weight loss as a number or percentage of weight loss to the nearest, should be whole percent. And this is the kind of thing the independent sample t-test can do. In diet A, maybe we had a mean percentage loss of 10%. In B, we had a mean percentage loss of 15%. Maybe we use body mass index. Maybe we use pounds lost. I think many would consider Um, Percentage weight loss might be the best way to measure this, but we can do it in a number of ways. But at any rate, this t-test, the independent samples t-test, could do this. It could compare the mean difference between diet A and diet B for our two groups. But what about if we do a second study? We're still studying weight loss, but as our participants join, we at random assign them to one of five groups. We have the Nutrisystem diet, the South Beach diet, the weight loss diet, Weight Watchers diet, the keto diet, and the regular diet. 5 different diets. They come into our room. You could consider it that way, or they consent to participate, and we at random assign them to one of these 5 groups, and we run a study. And this is what we're actually doing. If you think about it, we have these 5 diets. We'll just list them here for simplicity. Diets A, B, C, and D, and E. We follow them for the length of our study. Maybe it's 6 months. We get our average percentage of weight loss for each group. 8%, 10%, 12, 15%. The fifth group had no weight loss. And we want to compare all of these in one test. We can't do that with a t-test, but we can do it with an ANOVA. And in this case, this would be a one-way ANOVA. The one-way means we only have one independent variable. And in this case, it's diet. We have 5 conditions of that independent variable, diet, but it's still one independent variable. I've had students have trouble with this, so I want to share with you an example of what the difference would be. Supposing for our study, instead of just studying diet, we want to study exercise. And what we're going to do is we're going to have all of our patients wear a watch. And that watch will count the number of steps they take each day. And so we're going to divide our group up into those that walk 2,000 steps a day, maybe 6,000 steps a day, 10,000. So anybody 0 to 2,000, we'll call them non-exercisers. Anybody that's 2 to say 5, we'll call them low-level exercisers. 5 to 10,000 maybe are exercisers. 10 to 15,000 or more, whatever, would be maybe heavy exercises. So we're going to have 2 independent variables. We're going to measure and compare diet, and we're also going to compare different levels of exercise. That's what 2 independent variables would look like. 2 completely different things, diet and exercise. But here, even though we have 5 different treatment groups, those are conditions. The Nutrisystem, the South Beach, and these diets are conditions within one independent variable called diet. So make sure that's clear. If it's not, let me know. But this is how I like to try to explain it, and we wouldn't necessarily do this, but imagine we're meeting in the cafeteria of the hospital. As our patients come in, we give them a t-shirt. The Nutrisystem group gets a red t-shirt. South Beach, you get a blue at random as they come in. It's just we have all of our shirts in box. We just at random pull a shirt, give them that color. Okay. Now we're sitting in the meeting room in the hospital cafeteria, and they're all kind of in their groups. The red shirts are on one side, the blue shirts on another side. They're all within their groups, and we go over and we tell the people wearing the red shirt, okay, you guys are going to be on the Nutrisystem diet. And as I'm looking at that group of people wearing the red shirts, is there a variable? Is there a variable if they're all getting the Nutrisystem diet? And I would suggest to you there is not. It's a constant. They're all getting that treatment. But if I look at the whole group, I have 5 different types of diets that we're going to be giving out to our study participants. So diet is an independent variable. It can vary. It can vary in one of 5 ways in this situation, any of our different diets. But within each group, wearing all the same colored t-shirt, that's not a variable, that's a constant. And I think what a lot of my students over the past have tried to do is this. They look at each of these and they'll say there are 5 independent variables here. They're saying, well, This group is either getting the Nutrisystem diet or they're not. The next group is getting the South Beach diet or they're not. But that's really not the way that we look at this. We think of the independent variable in this case as being something that covers everybody, in this case diet, and it has these 5 conditions or treatment groups. And each of those treatment groups within that group is a constant. It's not a variable. So I hope that helps to clear that up. By the way, we call this a one-way ANOVA because there is only that one independent variable, in this case diet. If we had diet and exercise, as I mentioned, that would be 2 independent variables. For that, we'd run a two-way ANOVA. And we have actually a test called N-way ANOVAs, where we can have many independent variables having each many different conditions. And the ANOVAs can do that. They can run all of these comparisons at one time. And I want to show you this. Just to kind of try to encapsulate this. So let's look at this. This is the difference between a t-test and an ANOVA. In our first study, we had participants in a weight loss study, and they only had one of 2 diets. They had the keto diet or the regular diet, and that's all the t-test was doing. It was comparing diet A to diet B. Again, if it helps, the t-test cannot multitask. It can only do that one thing, make that one comparison. But in our last example of a study where we had 5 different diets, all being compared at the same time, this is what our one-way ANOVA was doing. Each of these letters represents a different diet. So it's comparing the A to the B, the A to the C, the A to the D, A to the E, B to the C, B to the D, B to the E, C to D, C to E, and D to E. I count 10 different comparisons, all in one test, all at the same time. When you think of the ANOVA, think of a multitasker. What the ANOVA did in this one test, and again, I want you to imagine this. I've entered the data into SPSS, press a few buttons, I did a t-test. Then I took this other study, the data, same thing, entered the data, pressed a few buttons with my one-way ANOVA, got my results. It would take 10 t-tests. I'd have to run 10 different t-tests to make all these comparisons that I can do in one ANOVA. And this is what you'll read in a textbook. When you think about these tests, imagine that each test has a little bit of error. Okay? We run a t-test, we get a p-value, it might be a little off a little bit, right? There might be some error in that. Might not be exactly correct. We have a p-value of, say, 0.01. It actually might be a 0.02. It doesn't matter. It's below 0.05. We'll take it. We'll say we have significance. We'll reject the null. But imagine now if we're off a little bit, if there's a little bit of error in any test, and we ran 10 t-tests, our error rate, or our margin of error, would be 10 times higher than running one simple one-way ANOVA. And that's the strength of the ANOVA, being able to make so many comparisons all at one time, many different independent variables, many different conditions, all being tested at the same time. The work of 10 t-tests in one test. Within the ANOVAs, we have a tremendous number of tests. I've already mentioned some of them. If we have one IV, it's a one-way ANOVA. If we have 2 IVs or independent variables, we can have a two-way ANOVA. And we can go on. We can have many independent variables. And so we have what's known as the N-way ANOVA, where the N is the number of independent variables we have. We can have a study where, if you remember, in the paired samples t-test, we were comparing a pre-condition number. Like I suggested, we had a group of patients on a regular diet. We knew how many pounds of weight they had lost. Then we put them all on the keto diet and see how many pounds they lose. And so we have 2 comparison numbers for each of our participants, the pre-score and the post-score. The repeated measures of ANOVA, though, can measure the dependent variable at really an unlimited number of times in a study. So, again, imagine this situation. We have a weight loss study. We have two different groups. We give them both different diets. We measure them before and after. And so we have those points in time. But supposing we were running this study that we had before, I want to get back to it. Sorry about that. We have this study again. We have the Nutrisystem, South Beach, Weight Watchers, Ketone Regular Diet. We have our groups, 5 different diets. We want to study them all at the same time. But imagine this. We have kind of a hunch that maybe the keto diet, you lose a lot of weight the first month, and then you taper off and you don't lose much. And I'm not saying this is true or not. I'm just using this as an example. That supposing we have that hunch. Whereas we think diets like South Beach and Weight Watchers, that a person gets on it, they kind of start to develop some consistency in their diet. Maybe they start off a little slow. They get with the routine. They're very happy. They go along. Maybe they lose more and more weight as the months go by. Maybe the Nutrisystem diet is such that patients get on that, they lose a certain amount of weight, and they're very consistent throughout the study. So maybe what we want to do is maybe we want to measure weight loss we want to measure a patient's weight at the beginning of the study, and then say every month for 12 months we want to see which of these diets is performing better, which is losing more weight, all along the way every month. That's what a repeated measures ANOVA can do. It can measure the dependent variable at various times throughout a study and see if there's any change in weight loss comparison. So we can measure all of our patients every month. At the end of the study at 12 months, we put all of our data into SPSS, run a repeated measures ANOVA, and it can tell us if there's any difference in the diet at any point in time during the study. For the ANOVA, just like the t-test, all the ANOVA can do, though, it can only make comparisons in means. It can't make comparisons with ordinal or nominal level data in our dependent variable because with those we cannot calculate a mean. So, if our dependent variable is not measured in scale data, we cannot run an ANOVA. The substitution for the one-way ANOVA, if we have ordinal data, is the Kruskal-Wallis. And if the dependent variable is measured in nominal data, we can use chi-square. And so it gets very complicated, but this is just the output from SPSS for one ANOVA, a one-way ANOVA. And what was going on with this study was that they were looking at the length of stay, LOS. I remember running this study for 3 different diagnostic groups. It doesn't really matter what they are, but they're actually from an older version of the ICD-10. It's diagnostic code 291, 292, 293. And we were interested in seeing if there was a difference in mean length of stay for each of these 3 diagnoses. What we have here, the important data comes out to us in SPSS in these 2 tables. Here in table number 1, we have the mean length of stay, and you could see the numbers 8.8 to 6.2 to 4.6, and the total mean was right at about 7 days for patients in those diagnostic groups and for the total group of some 390 patients. And by the way, that's what the N is. You can see the number of patients having each of these diagnostic codes. The other thing that's interesting, perhaps in this, is here we have our 95% confidence interval again. And remember, this is an estimate of the population mean. We only know the mean of our sample, but we can estimate it for the population. And what this is saying is that if we studied everybody in our hospital, the population from which the sample was drawn, if we studied everybody with diagnostic code 291, we think their mean length of stay would be between 7.77 and 9.89, and you could see the numbers for these other different diagnostic groups. So let's just look real quick. This is what is interesting about the confidence interval. We see that the 8.83 does fit between the upper and lower bounds of our confidence interval. It is between 7.77 and 9.8. The second diagnostic code fits in okay, and so does the third. It is possible to actually have a mean that's outside of that confidence interval because remember, the 95% confidence interval simply means that we're 95% certain that if we measured everybody in the population, that the mean for the entire population would be within this range. We're also given the minimum and maximum. So for diagnostic code 291, we had a patient that's length of stay was only 1 day, and somebody got up to 47 days. So that's what the minimum and maximum numbers are here for each of these groups. The second thing we get from SPSS is our exact ANOVA calculation output. In another class, we talked about degrees of freedom, that's the DF. And from running an ANOVA, we get something called the F statistic. And all that happened here was SPS gave us this, but SPS calculated with a degrees freedom of 2 and an F statistic of 19.715, we had a significance of P equals 0.00, which means there is a significant difference in the length of stay for these three diagnostic groups. And we can see that. It does look like that if one group was close to 9 days and another group was close to 5 days length of stay for average. So that's the kind of output we get with our one-way ANOVA. In the prior session, we talked about chi-square. Again, remember when we look at chi-square, I don't consider it to be a test of associations, correlations, or relationships because we don't get an R value. All we basically get from all of this, we get our cross tabulations, we get the frequency of those in each of our 4 cells, our 2 different diseases and the satisfaction, if they were satisfied or not. But all we really get is this p-value of 0.610. And again, that was determined from the chi-square value that was calculated, the 0.260, degrees freedom 1. Those numbers are only used to calculate the p-value, but in and of themselves, these 2 numbers don't matter. But the point is, this is how the p-value is calculated. With a chi-square value of 0.26, degrees freedom 1, we get a p of 0.61. So this concludes part 3 of our discussion of our comparative tests.